In the vast expanse of the cosmos, amidst the swirling galaxies and twinkling stars, lies a hidden world of patterns and shapes. Just as astronomers strive to unveil the secrets of the universe, computer scientists have embarked on a quest to understand and interpret the visual world through the lens of artificial intelligence. At the heart of this endeavor lies the challenge of object detection, the ability of machines to perceive and locate objects in images and videos. Imagine a telescope that could not only capture the light from distant stars, but also decipher the celestial tapestry, identifying planets, nebulae, and galaxies. This is the promise of object detection, a technology that has revolutionized fields like robotics, autonomous driving, and medical imaging. Among the many tools in the computer vision arsenal, the histogram of oriented gradients, HOG, stands out as a powerful and elegant approach to this fundamental problem. HOG is not merely a mathematical algorithm, but a testament to the ingenuity of human thought. It allows computers to see objects not as collections of pixels, but as meaningful entities defined by their shape and appearance. By analyzing the distribution of edges and gradients within an image, HOG transforms raw pixel data into a rich representation that captures the essence of an object's form. This essay embarks on a journey into the world of HOG, exploring its history, principles, and applications. We will delve into the ingenious ideas that underpin this transformative technology and witness its impact on our increasingly automated world. Join us as we uncover the secrets behind HOG and its remarkable ability to make the unseen visible. The quest to understand and replicate human vision has captivated scientists and engineers for decades. Early attempts at object detection often relied on simple features like edges and corners, rudimentary building blocks that provided a glimpse into the structure of an image. However, these methods struggled to capture the complexity and variability of real-world objects. In the annals of computer vision, the year 2005 marked a pivotal moment with the publication of a groundbreaking paper by Navneet Dalal and Bill Triggs titled Histograms of Oriented Gradients for Human Detection. This seminal work introduced the world to HOG, a novel approach that harnessed the power of gradient orientations to represent object appearance. But the story of HOG begins even earlier, with the pioneering work of Robert K. McConnell at the Mitsubishi Electric Research Laboratories in the 1980s. McConnell's research laid the foundation for gradient-based image analysis, paving the way for the development of HOG. His insights into the significance of edge orientation in visual perception would later inspire Dalal and Triggs to create their groundbreaking algorithm. The introduction of HOG marked a paradigm shift in object detection. Unlike previous methods that relied on simple features, HOG captured the essence of an object's shape by analyzing the distribution of edge orientations within its boundaries. This innovative approach proved remarkably effective, particularly in the challenging task of human detection, where it achieved unprecedented levels of accuracy and robustness. Imagine looking at a distant galaxy through a telescope. You might not discern individual stars, but you can perceive its overall shape, a spiral, an ellipse, or an irregular blob. Similarly, HOG allows computers to recognize objects by their shape, not by analyzing individual pixels, but by understanding the overall distribution of edges within the image. At the heart of HOG lies the principle that local object appearance and shape can be characterized by the distribution of intensity gradients or edge directions. In simpler terms, HOG focuses on how much the brightness of pixels changes in different directions. These changes in brightness, represented by gradients, provide crucial information about the object's boundaries and texture. Consider the silhouette of a cat against a contrasting background. The edges of the cat, where the background abruptly transitions to the cat's fur, are marked by significant changes in pixel brightness. These changes create strong gradients that HOG can detect and analyze. By quantifying the orientation and magnitude of these gradients, HOG builds a robust representation of the cat's shape, enabling it to distinguish it from other objects. The brilliance of HOG lies in its simplicity and effectiveness. By focusing on the fundamental building blocks of visual perception, edges and gradients, HOG provides a powerful and computationally efficient way to represent and recognize objects in images. To understand the inner workings of Hog, imagine a group of skilled artisans meticulously crafting a mosaic. Instead of colored tiles, they use gradients as their building blocks, carefully arranging them to create a representation of an object's shape. This process of transforming an image into a Hog descriptor involves several key steps. First, gradient computation. The first step is to calculate the gradient of the image. This involves measuring how quickly the brightness of pixels changes in both the horizontal and vertical directions. Think of it as identifying the slopes of the image's brightness landscape. Second, orientation binning. Once the gradients are computed, they are grouped into orientation bins. Imagine dividing a circle into several slices, each representing a specific range of angles. Each gradient is assigned to a bin based on its direction, creating a histogram that represents the dominant edge orientations within a localized region of the image. Third, descriptor blocks. To capture spatial information, the image is divided into small cells and a histogram of oriented gradients is computed for each cell. These cells are then grouped into larger blocks, and the histograms within each block are normalized to account for changes in illumination and contrast. Fourth, block normalization. Imagine adjusting the brightness and contrast of each block in the mosaic to ensure a consistent appearance. Block normalization achieves a similar effect, ensuring that the Hog descriptor is robust to variations in lighting conditions. These steps, working in harmony, transform the raw pixel data of an image into a rich and informative Hog descriptor. This descriptor, a tapestry woven from gradients, captures the essence of an object's shape, enabling computers to recognize and locate it within a scene.